welcome everybody to this series of lectures on the microprocessor and the microcontrollers. I am Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering, IARE, Dundigal. So today the topic which I am going to cover is Programmable Communication Interface 8251 USART. USART means Universal Synchronous Asynchronous Receiver Transmitter. This is used for serial communication. Basically, the communication is of three categories. One is simplex communication, half duplex communication, and full duplex communication. In simplex communication, the communication is only one way. For example, the computer to the printer or the FM receiver. So here, the communication is only one way. Whereas in half duplex communication, the communication is both sides. So if A and B are the points, the communication can take place from A to B or B to A, but not at the same time. For example, walkie-talkie. Contrary to this, we have full duplex communication where the communication can take place between the 2 points simultaneously. So that is the full duplex communication. So 8251A, it supports full duplex communication. It is a programmable peripheral interface which is designed for synchronous or asynchronous serial communication. So this communication, another classification is serial communication and the parallel communication. If the 2 points are close by, then we can go for parallel communication running so many wires. But if the 2 points are separated by a long distance, then we go for the serial communication to save the material cost of the medium. And serial communication, in turn, it is classified into two types, asynchronous and synchronous communication. So what is asynchronous communication? In asynchronous communication, you have one start bit and followed by the bits, data bits, followed by the stop bit, and it also may include parity bits. Whereas in synchronous communication, a group of characters are sent which are separated by the sync pulses. So, as far as the speed of communication is concerned, it is very fast in synchronous communication, but the probability of errors is more in synchronous communication. So, to reduce errors, the characters are sent bit by bit, and parity bit also is included in asynchronous communication. And in synchronous communication, both transmitter and receiver, they are synchronized by a common clock. So 8251A, it supports both the synchronous communication as well as asynchronous communication. And it receives the parallel data from the CPU and it transmits serial data after conversion. And when 8251A is used as a receiver, it takes the serial data and converts them into parallel data by removing the start bit, stop bit, and the parity bit, and then it gives the actual packed bit to the CPU in parallel form. So this is the pin diagram of 8251. It is a 28-pin IC, and it is available in dual inline package, DAP. And this is the functional block diagram of 8251A USART. We have the data bus buffer, read-write control logic, modem control signals, transmit buffer, transmit control, receive buffer, and receive control. So the data buffer, it has 8 lines, and on these lines, the command words are sent by the CPU to the 8251A USART. And this data lines are also used to read the status of 8251A by the CPU. And read-write control logic, it has the signals read bar, write bar, and chip select signals. And these signals are used for writing or reading the data. So these are all the various sections of 8251A USART: data bus buffer, read-write control logic, and modem control blocks. These are there on the left side of the functional block diagram, which I have shown you just now. And the transmitter section and receive section are on the right side of the block diagram, which I have shown you just now. The data bus buffer, so this is 8-bit data bus that is used to read or write status or command or data. And this read-write control logic, it has the signals, chip select signals, C by D bar, write bar, read bar, and reset signals. And control register, this is a 16-bit register, and this contains two independent bytes, namely the mode word and the command word. And mode word specifies the general characteristics of operations, such as the baud rate or parity or the number of bits per character, like that. And the command word, it enables the data transmission or reception. So if you are configuring the 8251A as a receiver, the command word has to be chosen appropriately. Similarly, if you are selecting 8251A for receiver, you have to select the command word appropriately. And register can be accessed as an output port when the command or data pin is high. And the status register, it is used to read the ready status of the peripheral. So status register, it provides information regarding the register status and the transmission errors. Now the data register, this is used as input or output port when C by D bar is low. So when the chip select signal is 1, that means the 8251A is not selected, so it is in high impedance state. So when the chip select signal is active, then depending upon the C by D bar signal, various modes are selected. So when C by D bar is equal to 1, it is used to send the control word or to read the status word from accordingly. So if C by D bar is equal to 1 and if read bar is 0, so that means the status is read by the CPU. Similarly, if the write bar is active, then the CPU writes the command word to the 8251A USART. And when C by D bar is 0, then it is used for actual transmission or reception. So if C by D bar is 0 and if RD bar signal is active, then the CPU takes the data from the 8251A. That means 8251A is used as a receiver. And when write bar is active, then the CPU sends the data to 8251A for serial transmission. Now modem control signals are DSR, that means data set ready, DTR bar, data terminal ready, CTS bar, and RTS bar. So when the system is switched on, then the modem sends data. Then the modem, when the 8251A gives a signal, data terminal ready. That means the data 8251A is ready for transmission. So when modem is switched on and when then there is a proper carrier, then 8251A sends a signal, data set ready signal to the 8251A. Then when 8251A is ready for transmission, it sends the signal RTS, request to send data, to the modem. And when modem is ready to send the data, that means when it is ready for transmission, it sends green flag using CTS signal, clear to send. So when modem sends CTS signal to the 8251A, then actual transmission starts. So DSR bar, DTR bar, CTS, and RTS, these are all the modem control signals. And the transmitter section and the receiver section, both these sections are double buffered. There are two buffers. So coming to the transmitter section, when it gets the data from CPU, it is stored in the output. It is stored in the register. From register, which is nothing but a buffer, holding buffer. So from holding buffer, it is sent to P2S register, that is parallel to serial register, and the data is transmitted on the TXD line. Okay, and these are all the control signals: transmit ready, TXE, and TXC. These are all the TXC is the transmitter clock, TXE is transmitter empty, TX ready is the transmitter ready signal. So here you have a holding buffer. The CPU sends the data to the holding buffer. From holding buffer, it goes to P2S register, parallel to serial shift register. So when CPU gives the data first, it is stored in the holding buffer, and from holding buffer, it goes to the parallel to serial shift register. So when hold buffer sends the data to the P2S register, when it becomes empty, then transmitter ready signal is activated. So this transmitter ready signal is connected to the INTR of microprocessor. Then the microprocessor knows that whatever 1 byte of data it has passed on to 8251A, it is already being transmitted. So it puts the next byte into the holding buffer. And when both holding buffer and P2S register, when both of them become empty, when both of them are vacant, then transmitter empty signal is activated. Similarly, the receive section also is double buffered, and whatever data that is received on RxD data, it is given to the serial to parallel shift register. So this input register is nothing but serial to parallel shift register. From serial to parallel shift register, it goes to the receive buffer. So when all the bits are received, then the 8251A removes the start bit, stop bit, and parity bits, and it puts the actual data in packed form into the receive buffer, and the CPU reads this data in one go. So when all the data is received in the input register, then receive ready signal is activated, and RxC is nothing but receive clock. Usually RxC and TXC, they are tied together and they are connected to the system clock. And sync detect or break detect, when there is a loss of sync pulse, then this signal is activated. So this is the format of mode word for 8251A. So here we have S1 and S2. So depending upon the combination of that, the number of stop bits are programmed. If it is 00, that is not used. If it is 10, 1 bit. If it is 01, then 1.5 stop bits. If it is 11, 2 stop bits are used for transmission. And next is EP. EP is nothing but even parity generation. So if it is 1, it is even parity. If it is 0, odd parity. And if parity is enabled, then you have to program this bit as 1. Otherwise, you have to program this bit as 0. And for you can decide how many bits per character you want to use. If you are using 5 bits per character, then these 2 bits have to be 0, 0. If you are using 6 bits, then these bits have to be 1, 0. If you are using 7 bits per character, then these bits have to be 0, 1, like as is shown here. If it is 1, 1, then 8 bits per character. And you can select different baud rates depending upon the B1 and B2. So this is B2 and this is B1. If it is 0, 0, that means it is in synchronous mode. So that means the transmission takes place at the clock frequency. And if it is 0, 1, then the transmission takes place at Rx by 1. If it is 1, 0, then the transmission takes place at Rx by 16. Sorry, clock frequency by 16. This is the clock frequency. CLK by 1. This is CLK by 16. If it is 1, 1, then the transmission takes place at the frequency CLK by 16. Clock frequency divided by 16. So you can have communication at variable rates, variable baud rates. The next is the command word. So here, first is EH, that is error hunt mode. So if it is 1, it enables a search for sync characters. You know, in synchronous communication, a group of characters are sent which are separated by the sync pulses, and if it is 1, then this search is enabled for the sync character. Next is the internal reset. If it is 1, that means it makes 8251 in mode instruction format. And if RTS, it is for request to send, and D4, it is for error reset. So it resets the error flags, parity enable, OE, and frame error, FE. And next, SBRK, send break character. So if it is 1, it forces TXD low. If it is 0, then normal operation. And when 8251A is used as receiver, this bit has to be 1. This bit has to be 1. In case you are using 8251A for transmitter, then this bit has to be 1. So accordingly, you have to program it. So when you have two sections, receiver and transmitter, at both sides you have 8251, and accordingly you have to set this command word. And this is the data terminal ready signal. Next, this is the status word instruction format for 8251. The first is DSR. So this bit indicates that DSR is at 0 level. Next, we have the sync detector, then frame error. So frame error, this is set when a valid stop bit is not detected at the end of every character, and this is reset by the ER bit of the command instruction. And next is we have the OE. So this flag is set when the CPU does not read a character before the next one becomes available, and this is reset by the command instruction. The overrun character is lost, and this is a parity error. So this flag is set if there is an error detected in the parity, and this is set by the this can be reset by the ER bit of the command instruction. And transmitter empty, we have already discussed that the transmitter section is double buffered and the receiver section also is double buffered. When both buffers in the transmitter section are empty, then transmitter empty signal is activated, and when the holding buffer becomes empty, then transmitter ready signal is activated. Similarly, when the input register is has received all the data, then receive ready signal is activated. So this is a status word register format for 8251. Now let us see this program. Design the hardware interface circuit for interfacing 8251 with 8086 and set the 8251A in asynchronous mode as a transmitter and receiver with even parity enabled, and two stop bits, 8 bits character length and frequency 160 kHz, baud rate 10K. So write an ALP to transmit 100 bytes of data string starting at the location 200 and 500H. So the first one, I'll explain the program for the transmission. So the data which is to be transmitted is at the memory location with the base address 2000H and 500H. H. So this is in the data segment. And here he has told to use 2 stop bits. Okay, let us say for 2 stop bits you have to use 1 1, and if it is 1.5 stop bit, you have to use 1 0. Suppose let us say you are using 1.5 stop bit, then this becomes 1 0. Let us do it for 1.5 stop bit. Okay, 1.5 stop bit. So 1 0 you have to choose. Then even parity, it has been asked to go for even parity. So you have to program this bit 1, then enable the parity PE, then 8 bits per character length. That is a option that is that has to be used as per the problem. So these 2 bits have to be 1 1. And what is the clock frequency? Clock frequency is 160 kilohertz. Okay. And what is the baud rate? 10k. The required baud rate is 10k. So what is 160 by 10? That is 16. So the baud rate factor is 16. So you have to use this as 10 as per our format. So you see here, for 16 you have to use 10. So accordingly we have chosen 10 here. So what is the word? So 1011. What is 10? 8 2 1. So this becomes 11, right? So what is 11? 11 is B. So this word becomes 0 B E H, because I am using 1.5 stop bit. And here this is a hardware circuit. The hardware circuit, see, the chip select signal, it is connected to A1 to A7 lines. So what the address lines are: A7 to A7, A6, A5, A4, A3, A2, and A1 and A0. So here all these things are connected to AND gate. So when all these things are 1, then the chip select, the 8251A is selected, and A0 has to be 0 because we have put a bubble here, and A1 is X. Okay, so when A1 is equal to 1, then what is the address? It is FE. So when A1 is equal to 0, then it is F. This is F 110084. It is FCH. Okay, so this is for the command or mode word, and this is used for the transmission. This is for the transmission, and this is for command. Now this is the program. So we have FE and FC, and the mode word is 0BE. Okay. Now first let us initialize the data segment register with the base address. So what the base address that has been given in the problem is 200 and 500H is the offset address. So move AX 200H, then move DSAX and move SI 500H. And because you have to transmit 100 bytes of data, what is 100 decimal in hexadecimal form? So 100 decimal is equal to 64H hexa. So we are initializing the counter with 64H. Now move AL 0 BEH. So BEH is the word which we have formed just now. So this is 0 BEH for 1.5 stop bits with the even parity enabled for 8 bits per character format, and clock scale for 10 kilohertz frequency. So that is 0 BEH, and that you send it to the 0 FEH. Just now I told you that FE is the address for the command or mode. So out AL is 0 FEH. Then move AX 11H. So now we are loading with another command word, because we have to program the 8251A for the transmission. So when you have to program for transmission, so this bit has to be 1. So accordingly, we have put here move AX 11H. So we are enabling the transmitter, and that again you send it to the command register. So out 0 FEH AL. So now the 8251A is configured as a transmitter. Now in AL 0 FEH. So get the data from the 8251A into the microprocessor. So that means you are reading the status of the 8251A. And AL is 01H. So whether you have to see whether the transmitter is enabled or not. So if it is not enabled, we have to wait. In AL, so we have to wait. Then move AL SI. So if the transmitter is enabled, then take the first byte into the microprocessor. Then from microprocessor, the data is sent to the 8251A. And for sending data, what is the address? FCH, as I have mentioned here. So out 0 FCH AL. So the first byte of data is sent to the 8251A, and from 8251A it goes to the TXD pin, and the data is sent in serial form. And next we have to send the next byte of data. So the SA has to be incremented. Then decrement CL, because we have to put a counter to transmit 100 bytes. So we have to keep a track on that. So for that, we have to use CL register, which has been initialized with 64H. And jump no 0 wait. So as long as 100 bytes are not transmitted, then it goes to wait. And the moment all 100 bytes are transmitted, then we will be stopping the program. So this is how the transmission is done. And here the RXC and TXC, they are joined together, they are shorted together, and it is connected to the frequency 160 kilohertz. For the actual transmission, it starts at 10K, because we have programmed the baud rate factor as 16. And when the data has to be transmitted over long distances, then RS-232 logic levels are used. And RS-232 for transmission, you see here, this is the TXD, and in RS-232, normal TTL logic is logic 0 is 0 to some plus 0.5 volts. Logic 1 is 2.5 to 5 volts. Okay. Whereas in RS-232, we use logic 1, we use minus 12 volts, and for logic 0, it is plus 12 volts. So for that, we use an IC MC1488, which converts the TTL logic to RS-232 logic. So this converts the TTL signals to the RS-232 logic. So what is the supply voltage for this? Plus 12 volts and minus 12 volts to this. And when data is received from the medium, it is in RS-232 form, and that is converted into TTL form using this MC1489 IC. So this IC, this converts the RS-232 logic levels to the TTL logic levels, because the microprocessor can detect can interpret or can compute only TTL logics. So the RS-232 signals, when they are received, they are converted into TTL logic levels by MC1489, and they are finally given to the microprocessor. So in long distance communication, when the signal gets attenuated, there is a chance of losing the logic levels. That is why RS-232 logic are used, so which have more range. TTL is only 0 and plus 5 volts, but this here you have plus 12 and minus 12. So the swing is more, so there is less chance of attenuation, and the drive capability is more. The drive capability is enhanced by RS-232 logic. So we have covered all the essential features of serial communication. So using 8251A, so this is a USART. It provides it facilitates both synchronous communication and asynchronous communication, and it has three sections. Sorry, it has a sections, data bus section, and read-write control section, modem control sections, and transmitter and receive sections. And in the transmitter section, we have the parallel to serial shift register, and in the receive section, we have the serial to parallel shift register. And initially 8251A is configured using the command and mode words, and when actual transmission or receiver process starts, then C by D bar signal is made as 0. So when C by D bar signal is made as 0, depending upon the read bar and write bar signals, if write bar signal is 1, then it is used as transmission, and if it is if the read bar signal is 0, then it is used for the reception. If the write bar signal is 0, it is used for the transmission. Before USART, we had UART 8251, and that was used only for universal asynchronous receiver transmission. But 8251A is more advanced. This can be used for both synchronous as well as asynchronous communication. So with this, I conclude today's session on serial communication using 8251A USART. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.